Okay, so hi everyone. So one quick recall that on next Tuesday you're going to have the PyTorch lecture. Yeah? So I would strongly recommend that you attend the lecture by Bruce, and he's going to take you through PyTorch and how you can use it if you want to implement. If you want to implement or do gradient descent by PyTorch, so how you can use autograd there, which is a very crucial thing when you do your homework and your project. So we ended up here last session, not exactly here, a couple of slides next, but we ended up dealing with the fully connected feed-forward neural network. So this is a feed-forward neural network, right? Why it is feed-forward? Do you remember why we call it feed-forward? It's just going forward, yeah? One direction, great. And it is fully connected. Why? All the nodes are connected. Every neuron is connected to the neurons in the next layer. So this was the guy, and we had for every single neuron all of the weights connecting the previous layer to the next neuron. And every single neuron had also a bias. And we talked about this, that we can interpret this bias as a kind of weight for the dummy input 1, right? So we did it like this. And we kept on going and tried to just formulate everything, just basically give some notation. And then we ended up here, right? Yeah? So here. Now I am just drawing it here for you, just to recap one. So say this is layer L, OK? And this is the previous layer, layer L minus 1. First of all, if L equals by 1, then what is this layer? It's the input layer, right? Clear? If L equals by 2, then this is the next layer, the second layer, which could be still a hidden layer. But this guy is then a hidden layer, right? And then what we did, we just connect every single guy to this one. So now you imagine that I am focusing in one particular neuron. And the index of this neuron is J. So I start counting from top. 1, 2, 3, I got to neuron number J, right? And now, if I want to write down the output of this guy, which I am going to show it by Y of layer L at node J, or at neuron J. How can I write it? What it would be? No, just go ahead. The weighted version of these guys, right? So this guy is giving me at the output. So here I am saying Y of layer L minus 1 of node or neuron 1. So on till the last guy. So here I'm getting Y of layer L minus 1 of the last neuron, which is neuron number WL minus 1. And what is this WL minus 1? We define it to be the width of the layer, right? So this is the width of this layer. So we have 1, 2, 3 till WL minus 1. So every single neuron here is giving us one particular Y. We talked about this, that if L equals by 1, then this is input, and this Y is basically the data itself. But if we go further deep inside the network, this is a hidden layer, and this is the output of the neurons of the hidden layer, right? And then we can write down this guy in terms of these people, right? So every single guy here, I can write it down Y of the previous layer, index I, and then I'm going to write down the weight. And the weight, we use the notation W, so it's a weight of layer L. Here we have node J, which is the node that we are talking about at the layer L. And then at the other one, we have node I. Yeah? So this is what we get where it comes from the other layer, right? So I could be 1, 2, 3 till the last one, WL minus 1. So I'm going to just write it down to be the summation, I running from 1 to WL minus 1, right? And if I want to just use this notation, then I need to have one extra bias here, right? But we talked about this, that we can get rid of the bias by thinking of the bias here to be one extra dummy variable 1, or dummy node 1, right? And then we connect this guy also to this one. And then instead of running it from 1, we are going to run it from 0, right? And then when we talk about yl minus 1 at point 0, index 0, we simply mean bias. No, y. Y, what is it? Y, here I equals by 0. What is the output of this node? 1. So that guy is 1. And then w, the weight, j and 0 is bias. Great. OK, so you got the idea. This is how we're going to formulate everything. And then you can look at everything. We talked about this, that you can look at it as a inner product. Yeah? And no surprise, because I mean, this is basically a neuron, like a perceptron, right? So you have your input, which is the output of the previous layer, multiplied inner product with the weights, which you have here, all of these guys. And then the inner product going to be this summation. Yeah? And this is what we're going to get as z. But then if we want to calculate this y exactly, the next thing that we need to do is to just activate it, right? So we're going to apply, we get the whole thing here, and we pass it. Oh, I didn't do it right. OK, maybe I can write it down here. So here is y, l, j. And this guy is going to pass through the function f, l, right? So the thing that I'm going to do is to calculate those guys, so these people, and I'm going to call them from now on z. So this is z of layer L at neuron j. And then I just activate this guy, right? So this is going to be your activation, or the output of your neuron in the next layer. Clear? So you do get the idea how it works. Yeah? So, and you need to keep on going till you get to the output. Clear? Now, one thing. If I am looking into this layer, so I just talked about the particular neuron or particular node index j. But how does j look like? So I have the first neuron here. So here is fl, and j equals by 1, and so on, till the last guy. So again, I have fl. And here, j equals by, what is it, the last one? W? L, the layer L, right? This is layer L. I have WL different neurons here, yeah? So this is going to be the outputs. I mean, every single of them has one output, which is the output after activation, right? And this is the one which I have written you in this form. But if I want to pass this guy to the next layer, do I need to do anything else? I just add a bias, right? So I'm going to put one dummy 1 again here, right? And then I pass it to the next layer. Clear? Everybody's clear? Yep. OK, so the next thing that I'm going to do after activating, I have the output of the neurons. I put one dummy input at the top of that. And then again, I repeat this. So every single neuron in the next layer has its own vector of weights. I just multiply this with that vector. And then I'm going to have the next set of outputs. Again, one dummy 1. And I keep on going, right? Clear? Cool. So this is how it looks like. And now we can write down everything in form of an algorithm. So I would start with the input. So I'm going to look at the input. So I have my data, x1 to xn. This is the points in my data point. And then I just add this dummy 1 here. And then I'm going to pass it through the first layer, right? So the first thing that I'm going to do is I am going for calculating the next z. So for every single neuron here, a neuron starts from 1 to the last one in the layer, so 1 to WL. I'm first calculating the affine transform, so this is going to be z times the corresponding weight vector times this YL, right? So the output I had from the previous layer, I just multiply that with the corresponding weight of every single neuron in the next layer, and then I calculate this affine transform z, right? And then the next thing that I should do is to just activate it, right? So once I calculated the affine transform, then I pass it through the activation function. Now I get my activated version, right? And now I want to go for the next layer. Before I go for the next layer, what should I do? The bias, exactly. So I'm going to add this 1 at the point 0. So this guy, again, I add it here. And then I keep on repeating this till I finish with my last layer. So when I get at this layer, I do the calculation for the next layer. And now I have everything at the output, right? Clear? And now when I am finished with the whole calculation, what would be the outcome of this algorithm? No?
Both the outputs of each individual layer and then the weighted sum matrix.
Sorry?
So it's both the weighted sum at each layer.
At each layer, exactly. So you're going to keep all of those affine transform and activated versions at each layer. You don't see it right now. You might think, okay, I'm only looking at the output. I don't care about those values being calculated in between. But as we're going to see, if you want to just calculate the gradient, you need to know them as well. Clear? So this is what we call it the forward propagation algorithm. Okay? Everybody's clear how it works? So nothing weird. I mean, it's basically just a bunch of products and sums, right? This is basically what the neural network is. Okay, now one thing that I can do to just ease the notation here for you, and we are going to stick with that from now on, is that I can even write it down in a more compact form. Now, how can I do it? Let's look at the output here, okay? So let's just look at these z values, these affine transforms, which are basically the inner product of those weights with the output of the previous layer, right? So each layer has its own outputs, so I'm going to get those outputs and then multiply it with a weight vector, right? So I now want to just write down the z values for the next layer. So I can put them next to each other. So I can say z of the first neuron in layer L, z of the second neuron in layer L, and so on till the z of the last neuron in layer L, right? Now, I'm going to expand it, so I'm going to use the same expression we had here. So exactly this expression here. So I'm going to write it down here. So it's going to be, for the first one, it's going to be its own weights multiplied with the output of the previous layer, right? For the second one, is the same thing till the last guy. Now, can I take this YL out of it? Can you represent that expression here, the last expression, more compactly?
You take the YL minus 1 outside and you get the matrix?
Exactly. So what you can do, you can just take YL minus 1 at the output. Just look at this matrix vector product. How do you calculate it? You get every row multiplied with YL minus 1, and then you're going to put it there, right? So this expression that I have here is basically matrix vector product. And what is the dimension of that matrix? How many rows do I have first? How many rows? WL, width of layer L. Yeah? How many columns do I have? 1 plus WL minus 1, right? So the dimension of this guy is, you look at the rows. Rows start from 1 to WL, so you have WL different rows, right? And now, how many columns you have? You basically start from 0 because you want to take into account the bias, right? And you don't need to memorize anything. You always see it immediately on the neural network here, because how many inputs you have here? Like this is layer L minus 1, this is layer L, for example. How many inputs you have? You have WL minus 1 plus 1, yeah? So this is going to be your number of columns, right? And how many outputs you get at the next layer is WL, right? So it is going to be your number of rows. So you're going to write it down in this form. And now the good thing is that you can represent all the weights within one matrix, right? And the matrix dimension is the number of inputs coming from the previous layer as the column, and the number of outputs, which is the number of neurons in your current layer, as the number of rows, right? So you can write it down in this form. Just keep in mind that it has lots of weights in it, right? So it's not a single vector or a single number. It's a matrix of weights. And now I can write down the forward propagation much compactly in this form. So I'm going to start from the very first layer, so the input layer. When I am in the input layer, I am going to just calculate the first affine transform of the first hidden layer by multiplying the whole matrix, meaning that the weights, every weight involved in between the input and the first hidden layer, multiplying it with the first layer output, which is basically my data. I calculate this z value, so the affine transform, and then I just do activation. I just pass every single entry of this vector z through that activation function, right? And when I did that, I should keep in mind that I need to add one extra dummy variable on top of it, which is the one counting for the bias, and I keep on doing, right? Clear? Now, how you can think of it now, you can think of your input as a kind of vector, multiplying it into a matrix, activating it, passing it through a nonlinear function, you get a new vector, right? You again multiply that vector into another matrix, you get another vector, you activate it, and you keep on doing till you get to your output, right? Clear? So this is going to be your forward propagation, and at the end of the day, what you need to keep all those z and y values, every single vector in these transforms before and after activation. Because as I told you, if you want to calculate the gradient, as you're going to see shortly, you need them. If you don't have them, you cannot calculate the gradient. Okay? So our output in forward propagation is not simply the output of the very last layer. It is the output of every single layer before and after activation. Clear? Any questions? No question? Yep. The whole conclusion is that, I mean, I think I have, okay. The whole conclusion is that I just wanted to tell you, I mean, I could initially start with that how a neural network works. You have your input, and then you multiply it with a matrix of weights, and then you activate them. You get your first layer output, first hidden layer output. Again, you repeat the same thing with a new matrix of weights, and then you again do activation, and you keep on going till you get to your output, right? This is basically what I wanted to show in the forward propagation. The only thing that I indicated was that this matrix of weights are simply the matrix of those, weights connecting every single guy here to every single guy in the next layer. Okay? Just wanted to indicate that, so open up the calculation for you. Are different. Yeah, every single of them. So each entry in each of these matrices is a variable that you can design. Okay? Clear? So, any questions? So we are going to stick to this guy because this notation is much easier, but I hope that this notation is now completely clear for you. Okay? Cool. So if it is clear, then let's go for a bit of more compact diagram, which is going to help us a lot. So since I am representing everything in form of vector matrix product, I can even compact this diagram. Okay? So I can think of this whole thing here as one vector, this whole thing here as another vector, and every single vector here is multiplied first with a matrix and then activated giving me the next vector, right? So I can simply write it down in this form. Yeah? So I have x. This guy is now a vector, right? And this vector is multiplied with one matrix of weights. And then I get a new vector. I activate it. And I repeat this till I get to my output, right? Clear? And then these matrices are the things that we can design. So again, when we are going to minimize our empirical risk or variables which are going to help us minimize that are these matrices. Clear? So we can design them. Now, so one thing, I mean, here is just one extra description that when you are doing, I mean, when you think of this particular transform here, after multiplying W to any input or any output of the previous layer, then after doing that, you just pass it through your activation function. And after doing it, when you get the new guy, you need to always add this 1, right? So you don't forget this adding 1 because I just dropped the bias, and you need to always keep in mind that there is one extra dummy variable there. Yeah? But it's not a very crucial thing, just when you want to implement. So WL basically is just the matrix of all the weights, and this FL block is basically the activation guy, which gets ZL, which is the transform after the passing through the WL, and then YL is the activated version. And you always keep in mind to just add this 1 when you want to transform over the next layer, right? Clear? So if it is clear, then we do know now, if we have a data, how we can pass it through the neural network, right? So we get the data, we get the vector of pixels, and then we send it over our neural network. It just gets multiplied to one matrix, activated, multiplied, activated, and so on, till you get one output which you want. But the point is that if you want this neural network to give you the output that you want, you do know that you need to train it, right? So if you want to train it, what do? You calculate the empirical risk, and then you try to minimize it, right? So if you want to do that, you need to calculate the loss, and then you just minimize that loss or risk, right? And if you want to minimize that risk based on what we had up to this point, we need to use gradient descent, right? Meaning that we need to calculate the gradient of the empirical risk with respect to what? Weights, all of those matrices, right? So that probably sounds a bit complicated, right? Because it's a kind of weird function passing through multiple activations. And then at the end of the day, you are calculating the risk. And you want to know what is the derivative of that risk with respect to every single weight in these matrices, right? So it sounds a bit complicated, but if we use backpropagation, then we can do it algorithmically very efficiently, okay? And if one thing is that you need to learn from deep learning course, that is backpropagation. And what I do now is that by the end of semester, many of you would be so pissed off on me because I am just keeping this backpropagation every single chapter coming back to you. But I'm sorry for that. I cannot avoid it. This is the only thing, the only reason that deep learning is working. If we didn't have backpropagation, we couldn't do the training because we couldn't apply or implement the gradient descent. Okay? So this is the most important part of the course to me, and this is why I'm just spending too much time on it. And we are going to have it like when we get again to CNNs, when we get to RNNs, we always have it. And if you want to test yourself whether you are, I'm going to tell it like, say it again at the very end of the semester. If you want to test yourself whether you have the intuition for deep learning, the first thing is that if you look at one architecture, you do know how you can backpropagate. And I'm not going to make you to do it from scratch by hand. I mean, you can use PyTorch, of course, for your project or anything, but you need to have intuition how you can backpropagate over that architecture. So just a kind of preface to tell you that this is a very important thing. Okay? So now, let's start with the backpropagation, and to do that, I need to do a bit of primary introduction to this stuff. So let's first look at the problem, the training problem that we have. Okay? So to do that, what I'm going to do, I'm going to look at the data set. And since I had like I and j a lot in this chapter, so I'm not going to show this with I anymore, so I'm using this b, okay? So b is the index. So I have x, b, v, b for b different guys, right? So I have 100, for example, data points. And I am also using v to refer to the true label. I mean, we used to use y, right? But I don't use y anymore because I want to show the output of my neural network with y. So no confusion. Clear? So this is the data set that you have. So x is the input, v is the output, yeah, the label. And I do not think anymore of the particular case of a scalar output. I think of a general vectorized output, right? So v could be in general m-dimensional, right? And what is v? V is the true output for x. What you want to do, your final goal is to make your neural network in a way that when you give x, you see v at the output, right? This is what you want to do. And to do that, you need to just design those weights, right? So this is the problem. And the way that we do it is that we just pass it forward. So this pass f is basically the forward pass algorithm that you had. You pass it forward, this xb over your neural network. So your neural network has this vector of weights, which is w. And what is this w? Is the vectorized version of all of those matrices. I'm going to show it in the next slide for you. Okay? But if you want to think about it, just you have lots of matrices, right? Start with the first matrix, put the first column vector, then the second one till you're over. And then you go to the next one, you collect the next one, and you are just increasing in size, right? Clear? So this is the vector which contains all the weights which are within these WLs in all the layers. And then what you're going to do, you are going to send your x through your neural network. You use forward pass. And then you can calculate the very output, right? And then when you get that very output, what you want? You want that very output to be exactly like your true label, which is here v, right? Clear? So what you want this xb after passing through your network going to give you yb, which is exactly your true label, right? And this is not going to happen at the very first place. So how we can do it? We basically go for training, meaning that we are going to calculate the loss between the output that we have calculated for every single point, the true label, then we average these losses over the whole data set that we have, and then we try to find w that minimizes this guy, right? This was the training problem. Clear? Now, you want to do the training problem, you want to solve this guy, and just to indicate where is w in whole formulation, because when you look at right-hand side now, you don't see any w. Where is w hidden? In y, exactly, in the output of your neural network, right? Because the output of your neural network is what you get after passing your data forward over this neural network, which is weighted by those weights w, right? Clear? So you want to solve this problem, which looks quite complicated, right? But if you want to solve it, the only solution, as I told you, feasible solution that you can use, is to use gradient descent, right? Meaning that you're going to start with some initial weights. So you initially set the weights in your neural network. Then you go ahead, you get into the loop, and each time you calculate the gradient of this risk guy, this whole expression here, you calculate the gradient with respect to all those weights. Yeah? The partial derivative of your empirical risk with respect to every single weight that you have in this big neural network. You calculate that, and after calculating it, you just move in the opposite direction of that gradient. You just change your weight, right? And then you get the new weight. You check if you're still changing the empirical risk, then you keep on doing that. So you get to the new point. At the new point, you again calculate the gradient, and you move in the opposite direction. You keep on going till you get into the minimum point. At that point, the algorithm stops. You have minimized your risk, right? Now, everything here is clear. The only thing that is not clear, how we can calculate this gradient. Okay? Now, let's start writing down this gradient. So if I want to write down this gradient, I can, first of all, look at this vector W. So I just check what is this vector W. I told you this is the vector of all the weights that you have. Meaning that if you start from your first layer, you're getting the first column, then the second column, then the, first row, second row, till the last row. Then you are finished with your first matrix of weights. You go for the second matrix, and you write the row vectors there, right? And you keep on doing till you get to the last layer, right? And every single of them is again a vector, right? So this is the vector of the weight for neuron J in layer L, starting from the previous input to the last input, right? So I don't want to confuse you. I just want to indicate that this matrix W includes all of them, and it's potentially very, very, very large. Clear? So forget about it that you calculate it analytically. Yeah? We need to find a good algorithmic way. So this is your matrix. This is your weight vector, or the parameter that you need to optimize over. And to do that, we need to just calculate that gradient with respect to this vector. If I want to calculate the gradient with respect to this vector, what should I do? I should get my empirical risk, and then I calculate the partial derivative with respect to every single weight, right? So every single of these weights, so every W, L, J, and I need to be able to calculate the gradient, the partial derivative with respect to that one. Clear? So if I want to write down my gradient gonna be the vector of these partial derivatives for all the values of I, J, and L, right? And I don't need to just confuse myself by writing down the whole vector. I can just focus on one particular partial derivative, right? Okay. Now, I'm writing that partial derivative, and now I'm going to replace this R hat, which is the empirical risk, with its definition. Okay? Now, looking at this side, can I just exchange the place of this partial derivative and this summation here? Can I do first partial derivative and then average them? Is it possible? Yeah, I mean, derivative of sum is sum of derivatives, right? So what I can do, I can write it down as, instead of first doing this summation and division and then doing the derivative, I can first take the derivative and then do that, right? Okay? So because of that, I don't really need to look at my whole data set, right? So if I can calculate this derivative, the partial derivative of the loss, for one single point in my data set, then I am able to calculate the partial derivative of the empirical risk. Clear? Yeah? So this is why all the textbooks, anything that you see on backpropagation starts with assuming that you have only one single point that you want to calculate is gradient, right? Or the gradient of the loss with respect to. Because you basically, if you know that one, then you average all of them, and you're going to get your gradient with the gradient of the empirical risk. So the key point here is that I need to develop one algorithm which is able to calculate this gradient, this partial derivative. The partial derivative of the loss of the output of my neural network and the true label for one single point in the data set, right? And once that I can do it, then I can do it for the whole data set. Clear? So that's it. And from now on, what I'm going to do, I am going to drop those indices B. Okay? So I'm going to focus on one single data point, so I have just one data point. That data point is x, so it's the vector of the inputs. And then that x passes through my neural network with weights w. And then once I get the output, which I show it with y, there is no index anymore for that one as well, then I calculate the loss between them. And the thing that I need to calculate is this derivative, this partial derivative, with respect to every weight that I have in that neural network. Clear? Any questions on that? Cool. So now that this is fine, now the only thing that I am left with is to now how I can calculate this guy. And if I want to calculate this one, the only efficient way that I can do it is backpropagation. And for that one, I need to start with chain rule. So if you got no question, let me start first with the chain rule, the idea of chain rule. And then, I do know many of you know it, but just to recap. And then after that, we can get to backpropagation. No question? So we're cool? Good. Great. So now let's start with the chain rule. And I guess most of you have had it at some point. Basic calculus. And I do know that you do know it very well, but just to give you the intuition again. Okay? So say I have a nested function. And what do I mean by a nested function? So say this z is a function of x. Say z is g of x. And then I give this z into another function like f, and then I get y as the output. So now, what do I say? I say y is a nested function of x, right? And now what I want to do, I want to calculate the derivative of y with respect to x. Yeah? So not always I can calculate this nested function in an analytic form, so the question is whether I can do it algorithmically. And I know that all of you know it, but we can easily do it with the intuition we developed with the gradients in the couple of sessions ago. So what can I say? I can start with z itself. I can say I have changed x for a very tiny bit, dx, right? If I change x with a tiny bit dx, then how would z change? It's going to be simply the derivative of the function g times dx, right? This is what we talked about. Derivative is simply defined as the tiny bit change in the input and the tiny change in the output. The ratio between them is the derivative, right? So if I change x with dx, then dz is going to be something of this form. Now, if I change the input of this new function, f, z, with the tiny bit dz step, then how does the output y change? This is going to be, the change in y is going to be simply the derivative of this function f at point z times the change in z, right? Now, if I replace this dz with the expression that I have here, I can say that the change in y is related to the change in the input x in this form, which is the multiplication of the derivative. So I'm going to first take the derivative with respect to z, and then the next thing is that I calculate the derivative of z with respect to the target variable, right? So this is the chain rule. Most of you know it. And what you can say that the derivative of your y, or the difference in your y, which is the derivative of your function with respect to x, this is basically this product. And we have this scalar form of the chain rule. So any change in y with respect to x, it's going to be you can always chain it in any form that you want, right? In this particular example, you can say change in y with respect to the middle variable z times the change in z with respect to the input variable x. And you can expand it in a general form, right? So if I have, for example, x giving me z1, and then z1 giving me z2, and then z2 giving me z3, and I keep on going till I get to y, and I want to calculate the derivative of y with respect to x, I always could say derivative of y with respect to x is the change in y divided by the change in x, which I can start with writing derivative of y with respect to the immediate previous variable, all right? dzn. And then I get from dzn to dzn minus 1, and so on till I get to the input, right? So this is the chain rule. All of you know it. The key point that I want to use here is this thing that we call it the computation graph. And because of the chain rule, we can use this graph to compute the gradient derivative on a computer easily. So what is this computation graph? Nothing specific. I mean, you start from your first variable x. You pass it through some function g. So this link here is a function. And the output is the variable which is given by the output of the function. And then I get again z1. I pass it through the next function. I get the next variable, right? And I keep on going till I get to my output. So every link here is a function. Every node here is a variable, right? And if I want to know, for example, what is the value of y, I need to put the value of x, and then it just gets computed over this graph, right? So this is what we call it the computation graph. Now, what is the useful thing about this computation graph? So as I told you, this is going to help us compute the gradient or the derivative of y with respect to any variable here in between using the chain rule. For example, say I have this graph and I want to calculate the derivative of y with respect to z. What should I do? I can simply say, what is the derivative of y with respect to, sorry, I said z, zn. This is f dot, right? So this is going to be f dot. So this is the derivative of y with respect to zn, right? Now, what if I want to calculate the derivative of y with respect to zn minus 1? What it would be? So if I want to calculate the derivative of y with respect to zn minus 1, I can say, look at the graph. So on the graph, I have zn minus 1. This guy is going to pass through gn, and then gives me zn. And then zn passes through f, and then I am getting y. So if I want to get back to this guy, I first calculate the derivative of y with respect to the immediate previous variable, then multiply it with the derivative of the immediate previous variable with respect to the next one, right? So I can write it down to be dy by dzn times dzn by dzn minus 1, right? And this is like I am going 2 steps over this graph, right? So I calculate, I do start from y. I calculate the first derivative. Then I calculate the next derivative. Now, if I want to get from y to this point, I just multiply anything in between, right? And if I want to get very back up to the z1, I just simply calculate all of those derivatives in between. So I jump from one node to the previous node, and I calculate the derivative. And if I want to know what is the derivative of the very end guy to this one, I just multiply everything in between, right? So this is going to be the computation graph. What I am saying from now on, I am saying that when I am calculating everything here, I am doing forward pass, meaning that I give x as the input, I pass it forward. I pass it through the functions to know what is y. And once I know y, I'm going to start to pass backward. So I'm going to pass everything backward to calculate the derivative. Clear? Everybody's clear? Right? Good. So one thing that you should pay very much attention to is that if you want to calculate the gradient, or I'm sorry, I keep saying gradient, but I think you know that by gradient I mean derivative here. So if you want to calculate derivative, you need to first pass forward and then pass backward. Yeah? So I hope that you are seeing it. If not, just pay attention. So let's first consider one example. Say that I have this kind of nested function. Okay? So I have this function where I start from x, I calculate z1, and then I get z1, I calculate z2, z3, and finally I get my output, right? Now, if I want to show it on a computation graph, how can I do it? Simply the thing that we had in the previous slide. So I can simply write it down in this form, right? Clear? So I can say that x is the input, then it gets multiplied by 2, giving me z1, then it gets a squared, it's giving me z2, then it's going to pass through exponential function, giving me z3, then through logarithm function, giving me the output. Clear? Now, if I want to know what is the output for the particular value half, how can I do it? I just start passing it forward, right? So I put the input to be half, then the first output going to be 2 times half, right? So it's going to give me 1. Clear? And then when I get 1, now I'm going to again pass it through this square function, so I'm going to get 1 again, right? And I again pass this 1 through the exponential function, I'm going to get e, right? And then I take the logarithm of this exponential function, I get back to 1, right? Clear? Now, if I want to calculate the derivative, what should I do? If I want to calculate the derivative, I should pass backward on this graph, right? So, look at this graph again. These are the functions, right? And if I want to write down these backward guys, can you tell me what they are? For example, what is the backward move from y to z3? Can you tell me? What is the derivative of the log function? It is 1 over the argument, right? So this guy, if I want, yes?
One thing in this course, when we see log, we automatically think the base is e.
Here you think base e, base e. It really doesn't matter. I mean, it just changed in a coefficient.
Because usually we see, if log e, then we see ln, ln.
Ln, oh, I see. Yeah, you can. Natural logarithm, yes. Yeah. But here you assume that this is simply natural logarithm, right? Yeah. So. Now, if I want to move backward, so this guy is going to be 1 over the argument, right? If I want to get from z3 to z2, I'm going to calculate the derivative of z3 with respect to z2, which is going to be the exponential function itself, right? If I want to get from z2 back to z1, I am going to calculate the derivative of the square function, which is 2 times z1, right? And then the last one, the derivative is simply 2. Clear? Everybody's clear? So everybody got this backward move. Now, if I want to calculate the derivative, what should I do? I should start by just putting those values which I calculated in the forward pass back to these functions, right? For example, if I want to know what is the derivative with respect to z3, I really need to know what is z3, and then I replace the z3 in this expression, right? So if I want to know what is the derivative, this backward pass from z3 to z2, I really need to know what is z2, and then I replace z2 inside that expression. Clear? So if I replace every single value here, for example, z2 here, z3 here, z1 here, and I mean, here the function is linear, so you don't really need. So if you replace all of them, back then you're going to have these backward messages, right? And now if you want to calculate the derivative of anything or y with respect to any of these guys, you simply multiply these guys to each other. Clear? So, for example, if I want to know the derivative of y with respect to z3, the last guy, I am going to multiply this one, just 1 over e, right? Derivative of y with respect to z2 is going to be 1 over e times the next guy, which is going to be now 1. Derivative of y with respect to z1 is this number 2 times the previous guy, which was 1, is going to be 2. And the last guy is going to be 4. Clear? Now, if here, when I wanted to just know these numbers, to start backpropagate over this network, over this graph, I really do need to know what are the values of z1, z2, z3, right? If I don't know them, I cannot calculate these guys, right? So this is why I told you, you need to first pass forward, calculate every single node on this computation graph, and then you can pass backward, right? So you can calculate the value of each backward jump on this graph. And then finally, when you want to calculate the derivative between 2 points, you just multiply everything in between. Yes?
For clarification, there's nothing necessarily stopping us from getting an analytical form of the backward propagation of the derivative with respect to any one given weight, right?
No.
We need to do the forward pass only if we actually want a value for it.
Yes,
but there's nothing stopping us from recalculating all of the...
Yes, but this is the point that I tried to somehow put in your mind. So you should think of it as a computer. So so a computer, how can it do it for you? It only can play with the numbers. It cannot do a symbolic calculation for you, right? So you're right. I mean, you can start writing down. I mean, if you write it down here, it's going to be 4x squared, and then these two going to cancel out. So from the very beginning to the end, you have you have 4x squared, and then the derivative is simply 8x, right? But your computer cannot do it. Yeah. You got the point?
Yeah, but now I'm thinking, well, these aren't going to be the actual sort of functions or weights in between layers.
It's not. We are going to build upon that. So we are going to just find out how we can really do this backpropagation over a neural network. That is a bit of work we need to do. But I hope you get the idea how you can calculate the gradient when you think of these x, z1, z2, all of them as variables on your computer, and then you start with giving x to the function in Python, and then you calculate for you z1, and then you give it to another function in Python and calculate z2, and so on. And now you want to move backward to know what is the derivative of your very output with respect to your very first input. And this is the way that you can do it. So for every of that function, you just define the derivative function, and then you once move forward, you have all the output values, then you move backward, right? So, clear? So I think this was a very, very good question your friend asked. So this is my whole purpose here, to just somehow plant this idea in your mind that when you are thinking of calculating gradients, you should think of numbers, not anymore about variables, which I mean, analytically they are variables and you calculate the derivative with respect to, but at the end of the day on your computer you need to calculate those gradients with numerical operations at one particular point, yeah? And you need one algorithm to do it for you, and that is backpropagation. Yes, you have?
I was just going to ask, wouldn't it be very inefficient to do this analytically because you'd have to do it for every layer, whereas with backpropagation you can use the result from the next layer to calculate the derivative of the current one?
We are going to do that, of course, but the point is that you need to know the derivative with respect to the weights of each layer, right? And because of that, you need to get to each layer in order to calculate that derivative.
I was just asking because you said that computers can't do things analytically, but I don't even think that's like the real problem. I think it would just be inefficient to do it because you'd have to do it for every.
Yeah, of course. But the point is that, I mean, you can think, oh, I get your point now. So you mean that, yeah.
Because you have to, like,
yeah, sure. It's a good argument, right? Right, yeah. It's also inefficient, of course, yeah, right. So, everybody's clear? Yeah? Great. So, now that you got the idea, let me see the time, okay. Now that you got the idea, I just want to indicate that if you want to do or move on the backward pass, you definitely need to first do the forward pass to have all those numbers. And then you can move backward and calculate the derivative. This is an important thing. And then I'm going to extend it to the vectorized form after a very short break. Yeah? OK, so 5 minutes. Thanks. So shall we go on? So we had this chain rule for the single variable case, so we can extend everything to the vectorized form, which is our target case, right? So what is it here? For example, let's start yet with one variable. So I have one particular variable x, and now I'm going to get this x and pass it through n different functions. So x is passed through g1, g2 till gn, and it's going to give you z1 till zn. And then you have one multivariate function f, which takes z1 to zn and gives you the output y, right? And now you're curious to know what is the derivative of y with respect to x. So we can extend the same idea that we talked about before. So we can start with just looking at every single zn. So I would say zn is going to change dzn, which is simply the derivative of the function times dx if I change my input with dx, right? Clear? Now, I have a multivariate function f, so y is a function of z1 to zn. And if you remember, when we have multivariate function, how do we think of the change at the input? In the form of a vector, right? So our change at the input is going to be a vector, and that vector is the vector dz. And that dz vector is basically d of z1, d of z2, and so on till d of the last guy, right? So this is the change that you can do at the input of your function f. And if you do that, if you do this change, dz, what is going to be the change in your output? Do you remember that? So if I change the input of that function f with vector dz. Now, dz is a vector. Look at it, dz. It's dz1, dz2, till dzn, right? So I have this vector. If I change the input of function f as this, what is going to be the change in y? dy, we can write it down in terms of dz, and gradient, right? So we now use gradient instead of that, yeah? So if you remember, we said that if we have a multivariate function f, which is a function of z1 till zn, if we just change every single argument with dzn, then we need to multiply that guy with this partial derivative, and then we sum them up. And this summation was simply the inner product of the gradient with the vector dz, right? You remember that? So inner product of your gradient. Now you have a multivariate function, so you need to calculate gradient instead of derivative, right? So now if I simply get this dzn here and replace it here, the thing that I'm going to see is this one, right? So what I can say that the change in y with respect to x, which is going to come out of this summation, is going to be the summation of the partial derivatives and the derivative of every single zn with respect to input x, right? So this is going to be the vectorized form. And the way that you can write it down is that you can look at y, and you say that it is a function of z1, z2 till zn. So I'm going to calculate every single partial derivative. And then for every single partial derivative, I'm going to calculate the derivative of that variable with respect to my target variable. Clear? Yeah? So if not 100% clear, let's look at the computation graph. That's going to make it much more clear for you. So what can I do? I can say that I have x, which is my input, and now this x is going to pass through n different functions, right? So it is going to pass through g1, g2 till gn, and it's going to give me n different variables, right? And those variables are all going through function f to give you one variable y, right? Now, if you want to calculate the derivative of y with respect to x, and if you want to think of it in form of the backward pass, how many paths do we have? We have n different paths, right? I can pass from y to z1 and then from z1 to x. I can pass from y to z2 and then from z2 to x, and so on till the last guy, right? and I should pass over all of them and add them, right? Now, on this graph, if I want, for example, to calculate the derivative of y with respect to z1, I can simply calculate the partial derivative of my function f with respect to z1, right? If I want to calculate the derivative of y with respect to z2, I would calculate the partial derivative with respect to z2. So you can pass backward in this graph from y to all of these z nodes by calculating the partial derivative of y with respect to that particular node, right? And then if I want to get back, for example, from Zn to x, what should I do? I calculate the derivative of Gn, right? So I'm going to get back by the derivative of Gn, right? And I can do it for all the other nodes as well, right? Now, if you want to get back from y to x, what should I do? I just pass backward over this graph. So f1, the first partial derivative, times g1. f2 dot times g2 dot, and so on till the last one. And then once I have all different paths towards my input, then I sum them up. So it's going to be of this form. So you have every single partial derivative multiplied with every single derivative on the other link, and then you sum them up. Right? So when you think of it in forms of a computation graph, that's going to be easier to write it down. Clear? Everybody's clear? Any questions? No question. Great. So if you got no question, then let's try calculating gradient of the single neuron. And what I want to do, again, just make it clear for you. As I told you, we have one input. We are going to pass it over our model. Just one single input. We are not thinking of multiple inputs right now. Just one single input x. We are passing it over our neural network. We get the output. We calculate the loss between this output and the true label. And then what we want to calculate is the gradient of that loss with respect to all the weights that we have in this neural network. So let's start with a simple case of a single neuron. Okay? Everybody's clear what we are going to do? So if I want to calculate the gradient, how many parameters or what is the dimension of my gradient? What is it? N plus 1, right? Because I need to calculate the gradient of the loss with respect to W1, W2 till Wn and the bias, right? So I want to calculate this gradient, and I want to use the computation graph. Okay? Now, just one repetition. X is passed. I got Y. I want to calculate. I first calculate the loss, and I am going to calculate the gradient. Now, the whole process of starting from X till ending up with the loss is what we called it. Help me on that. What is it? When I start with X and I end up calculating the loss. Forward pass. Great. So you pass it forward, right? And then we want to just move backward. Now, let's start with the computation graph. Now, one key question, what are the variables on this computation graph? Weights and bias, right? So I should start my computation graph with weights and bias, right? And what is the output? Is the loss, right? So I'm writing down R hat, but this R hat is basically this loss that I defined here, okay? So because I'm thinking of one single point, then the empirical risk for that single point is basically the loss, right? So R hat is basically, R hat here is basically the loss that I calculate between my output of the neuron and the true label. So this is my input, that is my output, and on the computation graph I need to learn I need to draw how I get from this guy to that guy. So if I have my weights, what is the immediate thing that I calculate in the neuron after knowing the weights? Just look at this, the guy. So you know weights and bias. What do? You multiply every guy with the corresponding x, and then you sum them up, right? And then what is the immediate thing that you calculate after that? It's z, right? So I am getting from these guys to z first, right? If I have z, then what do? I'm going to activate it, right? So I'm going to get from z, so I simply multiply everything here with the corresponding x, I get z, and then after z, I'm going to activate it. So I'm just passing this z over this activation function, f. So I am passing z through f, I'm getting y. And now that I have y, what is the last thing that I do to calculate the loss? I compare y with the true label v, which I have in my data set, and then I use my loss function to calculate this guy. So this loss function is going to give me this r hat, right? So this is the computation graph. If I fix my w at the input, all of my weights, then I am able to calculate the loss, right? Now, I want to now move backward. So how can I move backward? So forward pass is basically starting with a bunch of weights and calculating the r hat. And now, how can I move backward on this guy? I first need to move backward from the loss to y, right? So I'm going to move from loss to y. Can I do that? Yes? How do I calculate? So for example, this loss is y minus v squared, right? Then I can simply calculate the derivative, right? So if this is the case, then L dot is going to be 2 times y minus v, right? So I know my loss, I know that derivative. Clear? Yeah. Now, if I get here, how can I get back from y to z? I again calculate the derivative of my activation function. So I'm going to calculate that derivative, right? So if I am at z, then how can I get to b1, to b, to the bias? I need to calculate partial derivative, right? Because z is a function of b, w1, w2 till wn, right? Now, what is the partial derivative of z with respect to b? What is it? So it's 1, exactly. So just look at z. Z, you can write down z to be b plus w1 x1 plus w2 x2, and so on till wn xn, right? So the partial derivative of z with respect to b is 1, which we called it x0, right? The dummy variable. So that guy is going to be x0. What about, for example, the partial derivative of z with respect to w1? x1, great. So you see the point. So you can simply move backward to all of those nodes, right? Now, if I want to calculate the partial derivative of this r hat, the loss, with respect to b, what should I do? I just multiply everything, right? So I start from this point. I can say, OK, the derivative of the loss multiplied with the derivative of the activation function multiplied by x0, which is 1, it's going to give me the derivative with respect to b. Clear? Right? You see it? Now, if you want to be able to calculate these derivatives, you need to first move forward. So this is for the, I don't know, third time, fourth time. So keep in mind, if I don't calculate z and y, I cannot calculate L dot, because L dot is the derivative of this loss. Look at this one, for example. L dot, the derivative, is calculated at point y. I need to know what y is in order to be able to calculate that number, right? So I need to move forward and then backward. I cannot start from the end and move backward, right? So now, the derivative with respect to any particular variable, for example, wn. I can say this is the derivative of r hat with respect to y first. So it is going to be L dot, and then the derivative of y with respect to z, which is the affine transform, which is always f dot, and then the derivative of z with respect, or partial derivative of z with respect to that particular weight, which is going to be the particular x. Right? Clear? Everybody's clear? So now what you can do you can simply, I mean, if you start with this input, I mean, if you want to, for example, train this guy, how you can do it, you can start with any weight, right? And then you move forward, you calculate everything, you get to the output. You check your loss, it's not small, right? And then you calculate all of those derivatives, right? And then you move backward. You move backward, you get the gradient, right? You have the gradient, you update your weight, and now you have a new weight, right? You pass it again forward, you get the new loss. You want to minimize it, so you still need the gradient. You move again backward, right? You keep on doing forward, backward, till you don't need the gradient anymore. Clear? So this is the idea of, I mean, this is basically backpropagation for a single neuron. So I hope this is clear. Yeah?
I was wondering, this backward propagation is just only for implementing a gradient descent in our system, am I?
Exactly, exactly. But this is why, I mean, we can nowadays do it, right?
Yeah.
So
If it wasn't in this way, we couldn't solve the optimization problem.
exactly.
Yeah.
So if we didn't have backpropagation, we couldn't calculate the gradients properly. And if we cannot calculate the gradient, we cannot use gradient descent, so we cannot minimize the empirical risk, right? So minimizing empirical risk was known like in 50s, right?
Yeah.
But the algorithm which made us able to do that was backpropagation. When it was proposed, many people did not like it. So for a long time, for decades, people started to doubt it. Yeah? And then at some point, when in 2012, the AlexNet worked, then people finally believed that it's really working because it's just training something, right? So, yeah, but backpropagation is basically an algorithm that lets you calculate gradient. Yeah? It's not an algorithm for training. It's just an algorithm that lets you calculate gradient, and then the training is done by gradient descent, right?
You mentioned that people initially weren't convinced by the notion. Can you maybe talk about why that was?
Yeah, we're going to see it later. I mean, in chapter 5, I guess, because there is something called gradient vanishing.
Oh, and the gradient.
When you have a very deep network, this guy is going to get multiply, and those things that are getting multiplied, they could be very small, right? And at some point could numerically vanish, right? And then you really have no gradient.
I guess the opposite way, it sort of just explodes.
Yes, exactly. Or it could explode if you have big gradients in between, but then there is a way to solve it. But initially people thought like this is just some fancy thing which is not going to work numerically, but it started to work. Yeah?
So if the computer only deals with the numbers, why do we care about intermediate stuff? Can we just take the input and the output?
Yes, but I mean, if you want input and output, right, but here you have only, I mean, just pay attention, this is not the input to your neural network, right? This is your weight. The input are these x's, right? So if you want to calculate the gradient with respect to these guys, you need to get from r hat to these guys, right? And if you have connected them, I mean connected these instead of x's, you have output of another layer, you need to keep on doing this. So I don't want to confuse you right now. You're going to see it, I'm not sure today, but definitely by the next session. But the point here is that if you mean why we are calculating these guys, this is basically because this is easier for us. Because we do know what is the expression for loss, and then we can just define the derivative of loss. We do know what is the expression for activation. We can define the derivative for activation, right? But if you are asking why we are calculating, for example, like in multi-layer network, we are calculating for every layer, the reason is that every layer has its own weights. And you need to calculate the derivative with respect to those weights. So you don't care about only the weight of the very beginning, the first layer. All of them, right? Any questions? So everybody happy with backpropagation? If happy, why you are not excited? Like, okay, yeah.
I guess the other thing is, so the example you're giving is really for single neuron, but
Yeah.
the reason it would work in practice is because of how deep, how deep the network
Yes.
is. And you'd have to do it for every single weight and every single layer.
Exactly.
So by having the gradients from before, you can just more easily
Exactly, but when you write it down for these MLPs, you're going to see that backward propagation that you find is exactly the same as forward propagation, just changing, exactly, flipping everything, exactly. Yeah. But basically, any architecture that you can train, you basically know how to move forward and backward in every single module. So here I'm just thinking of fully connected simple networks, but when we get, for example, to the convolutional neural networks, we find out how we can move forward and backward on the convolutional layer, and so on for the other architectures, right? Any questions? Good. So if you got no question, then let's do a bit of linear algebra again. So we can extend everything that we had here in the vectorized form. So for example, I had this computation graph for you, and I am going to define this particular function g, which is now a vectorized function, meaning that it's a vector of n dimension, and every single entry of it is a function of x. So you give x, you get a vector at the output, right? So if I define it like this, and if I define the derivative of this guy, I haven't defined it yet. So if I have this g, then I can simply represent this factor graph, the computation graph that I have here. I can write it down in a more compact form again, so I can, instead of having all of those branches, I can use this notation, right? So I get x. Out of x, I have this on the link. I have this vectorized function g, which is going to give me the vector z, and then I get this vector z to function f, and that is going to calculate me y, right? And now if I want to move backward on this graph, what should I do? I need to calculate the derivative from y to z, and then derivative from z to x, right? So you can always move backward on any of that. The only thing that we should pay attention here is that what does derivative in this vectorized form mean, right? So for example, I can define the derivative of this vectorized function g in this form. So I can just put the derivative of every single entry next to each other. And now I'm going to call this dz to dx, right? So it's a vector of dimension n. Clear? Now, if I look at this one, so I'm getting from z to y, and z here is a vector, y is a scalar, is a number. If I want to calculate the derivative of y with respect to z, what kind of derivative do I have? A gradient, because y is a multivariate function of z, and then for every single entry inside z, I have a partial derivative. So how can I move back where I can say the derivative of y with respect to z, a scalar to a vector, it's going to be a gradient. Derivative of z to x, vector to a scalar, it's going to be a vector of derivatives. And now if I want to calculate the derivative of y, very output, to x, the input, how can I do it? I just multiply those guys, right? But the question is, how can I multiply them, right? Two vectors. So any idea? Yeah. Yeah, but here, what should I do? No, but here, what do you do? Just look at your dy to dx. What should it be? A number, right? It should be a scalar, because y is one number, one variable, x is one variable. So dy to dx, inner product, exactly. So it is, if you write down the chain rule, it's going to be in this form, and then you're going to see it to be an inner product, yeah? So usually what you can do, before I take you into the more details, usually what you can do, whatever you have, you can always draw this vectorized form of the computation graph, and then you can look at every two nodes. And then from one node to the other node, you're going to see how the derivative look like, right? And then when you write it down, now if you want to move from the very output to one of them, and you want to multiply them, you just should check the dimension. What kind of dimension you need, and then you're going to calculate it, right? And you might be happy you say that the guy, that's me, is going to leave us with that, and he's telling us this and immediately going to the next part, but I am not going to do that, right? So I am going to try it a lot for you to make it like obvious for you, but at some point I'm going to leave you. So don't worry. We're going to practice it, so I don't want to leave you here just simply by telling you that move backward on this. So we are going to do it really on the feed-forward neural networks, but the key idea is always that. Now, always draw the computation graph. Then when you want to move backward, just check the dimension, and then you can calculate the gradient or derivative with respect to any 2 points on this graph. Okay? The only thing that you should pay attention is always a product. The only thing that you should pay attention is the dimension. You're going to see it through this part of the course. So, okay, what is it then? Let me see. Yeah, this is basically what I tried to explain you, or what I said right now. I tried to explain it in words. That when you get from x to y, then backward, you'll see here you have a vector, another vector. Now you need a scalar from y to x so you can calculate the inner product. But we are going to deal with it much more in the forthcoming part of the course. So, right, now let's get back to this single neuron. And let's see if we can do the same idea, apply the same idea on this neuron, right? So if I want to vectorize everything here is pretty much vectorized, right? The only thing that I need to vectorize is this particular node, right? And what I can do, I can simply say that I define x, this new form of x, which is my x itself, and this dummy variable as the first entry. So it's going to be x. And then I have the vector w, which is basically the vector of all variables that I do have, right? And then what can I say? I can say that this computation graph looks like this one, right? So I get the vector of the weights, w. Then I inner product it with x, because this expression here, I'm multiplying b with every single entry on x, and then summing them up, it is basically the inner product, right? So I am going to inner product w with x, and then from that one, I'm going to get the scalar z. Then I activate it, then I calculate the loss, right? And now if I want to move backward, you do know how you can move backward from r hat to y. It's a simple derivative. From y to z, it's again a simple derivative. How can I get from z to w? What should I calculate? Should I calculate again a derivative? No? A gradient. Great. Yeah? So I need to calculate a vector of partial derivatives, right? So from loss to the output, it's going to be a simple derivative. From y to z, it's again going to be a simple derivative. But from z to w, I need to calculate the gradient. And when I calculate the gradient, then I can say the backward path is in this form, right? So I move forward, I calculate the loss. When I get the loss, now I calculate the first derivative, second derivative, the gradient. And now if you want to calculate the gradient of r hat with respect to w, you simply multiply everything here, right? Everybody's clear? Am I being too annoying today? Because nobody's... Yes?
I'm really confused about that. How they are going to work to optimize the problem.
Yeah, it's going to work. Yeah, this is basically what people initially thought. I mean, this is just a story. It's not going to work, but it worked. This is the whole point. And really, it just worked. Yeah, this is the point.
Would like to see an overview of them.
Yeah, we're going to do it. No worries. We're going to do it. So we're going to go over the whole neural network with that. Yeah? OK, so for example, in this particular case, if I want to calculate the derivative of z with respect to, or gradient of z with respect to w, what can I do? I can just write down z in terms of all of them, all of those w's, and then I just calculate the gradient, the partial derivative, which we do know that this is basically x itself. So I basically can replace this gradient of z with x, and I can say this is my backward pass. So I fix w, I calculate this forward pass, then I have everything on this forward pass, then this is going to be my backward pass, right? And then if I just write down the gradient of if I want to calculate the gradient of r hat with respect to w, I'm going to start from the very last point. So I'm going to calculate L dot, then I multiply L dot to F dot, and then I multiply L dot F dot to the gradient of z with respect to w, which is x. This is exactly the expression we found initially by going through the whole, larger computation graph that we had. Okay? Everybody's clear? Any questions? Any?
Particular reason you put F and then L?
Sorry?
Any particular reason you did F and then L instead of L, F, X?
No particular reason. Yeah, it should be L, you're right, L dot F dot X, that is better, right? So did I do it everywhere? Okay, it was just because of copy paste, sorry. No reason. Okay, so good. Now that you have the idea, I am very happy because I didn't expect to catch the schedule, but apparently I'm doing that. That's great. So now that we have it, what I want to do next, I want to just show you how you can do it in a very big fully connected feed-forward neural network. And if I want to do that, I need to first do some local operations. So this local operation is something I made up by my own, okay? So it's not a kind of technical term. I just made it by my own because I thought it is the easiest way that we can understand it. So what I'm going to think from now on, so you don't mistake it with a real neural network yet. We're going to get to that one later. So what I'm going to think, I'm considering r hat to be an objective function, and it's a scalar. So it is the loss, exactly the loss that we have in our neural network. But now, right now, you think that this is a scalar function. And this scalar function has been calculated out of y. Okay? So I have a vector y, and I have indicated here dimension k to just avoid you getting confused with the width of your layer or anything like that. So you have one vector y, and this vector y has passed through some function, some multivariate function, to give you r hat, right? And the thing that you do now is what the value of this gradient. So you do know what is the gradient of r hat with respect to y at the particular value of y that you have calculated, right? Now, what you want to do, you know that this y is coming from another variable. So there exists one other red variable passing through some sort of transform, giving you y, and then when you get y, then out of y you get your r hat. Now the question is, if you do know this gradient, the gradient of r hat with respect to y, so you do know how to move backward up to this point. Now, how you can move backward to this red variable in your graph. Clear? And now, what I'm going to do, you see here dots? I'm going to replace some different functions here. Okay? For feed-forward neural network, only 3 different functions. I'm going to replace them, and for every single of them, I am going to calculate this backward path. And once you do know these 3 basic functions, then you can move backward always on your neural network, at least the fully connected feed-forward neural network. Right? Clear? So don't mistake, this r hat is not, or y is not necessarily the output of your neural network. So just think of it general, right? So think that y is a variable coming from x. So there was this red guy. So there exists one red guy, just gave you y, and y gave you r hat. And you do know what is the gradient of r hat with respect to y. Now you want to calculate the gradient of r hat with respect to the red guy. Okay? So let's start with that one. So the first local operation that I'm thinking of is the entry-wise function operation. So what I assume that I have a variable like z, and this variable z is being passed through some function. What is that function in a neural network? That is the activation. Perfect. So in neural network, that is an activation function. But again, don't think of a neural network right now. Okay? So I have one vector z, and this vector z has passed through one function. So every single entry of z has passed through the same function f. And then I get y, and then from y I calculated r hat. Now, I can calculate the gradient of r hat to y. Now I want to know what is the gradient of r hat with respect to z. Clear? Yes? Okay. First of all, what is the dimension of z if dimension of y is k? It should be k. Great. So same dimension because it's an entry-wise function. Okay. So if I want to do that, I can simply start writing down the chain rule. So what I can say I want to calculate the partial derivative of r hat with respect to one of the entries in vector z, right? Partial derivative of r hat with respect to zk, entry k, right? So this entry k, is going to appear in entry k of this vector, right? So entry k of z is passed through function f and has given me yk, right? This is what I do now, right? Now, if I want to get from r hat to this guy, I get from y hat to yk, and then from yk to zk, right? So I can say partial derivative with respect to zk is going to be a partial derivative with respect to yk, multiply with partial derivative of yk with respect to zk, and this second guy is simply going to be the derivative of that particular function. Clear? Everybody's clear? Yes?
Can't you represent the f dot like by a diagonal matrix?
Yes, we can do it, but I'm going to do it much easier. Okay? So now, the point is that the partial derivative of r hat with respect to entry k here, it is going to be the partial derivative that I do have. So this is in my gradient, and then I multiply it with the derivative of f at point zk. Now, if I want to just calculate the gradient of r hat with respect to z completely, I just get every single entry in my gradient with respect to y and multiply it with f dot at point z, right? So it is going to be pointwise product of these two guys. And what do I mean by pointwise product? I mean that one. So if I get z dot y, I forgot equal here, sorry. So it equals to z, you just get every pair and you multiply them. Okay? And the moral of the story is that if you have such a graph, so if you start with some z, you pass every single entry through f, you get a new vector y, and from y you get to r hat. And if you do know what is the gradient of r hat with respect to y, then the only thing that you do need to do is to calculate f dot. You pass your z through this f dot, and then once you have it, you multiply this vector and this vector entry-wise. Clear? Everybody's clear? So that was easy, right? So what about the next one, right? What about the next one? So the next operation that I am considering is a matrix vector product, meaning that I assume that I have my z, this is a vector of some dimension, and then I multiply it with one matrix, which I do know it. That matrix is A. And then after multiplying with A, I am getting y, and from y I am getting r hat, right? And I do know what is the gradient of r hat with respect to y. I want to calculate the gradient of r hat now with respect to z. Clear? Now, one question. If matrix A has k different rows and n different columns, and y has k different entries, then what would be the dimension of z? It's n, right? So when you have a matrix, number of rows is going to be the dimension of your output at the product, and the number of columns is the dimension of your input, right? So z must be of dimension n, right? Z is of dimension n, y is of dimension k. A is a one matrix k times n. And n and k do not need to be the same anymore, right? Okay. Now, if I want to do that, what can I do? I can start by writing down one single y in terms of the whole vector z. So what I'm going to do, I'm going to say, okay, this is my vector z, which is z1 till zn. And this is going to be multiplied with one matrix A, and it's giving me one output y, which is y1 to yk. Yeah? And now I'm going to focus on one particular y, which is yk, this guy. If I want to calculate this one, what should I do? I'm going to consider row k, right? And multiply this inner product with the whole z, right? So this is going to be the thing that we have here. So one entry is the inner product of this. This is the row vector because I'm changing n from 1 to n. So I am calculating I'm considering all of the entries on the row k of matrix A and then multiply them with z, right? And then sum them up. Clear? Yeah? Now, if I want to calculate the gradient, the partial derivative of r hat with respect to zn, what can I say? I can say in general that this zn, in general any yk here, because every single entry here at this vector y1, y2 till yk, every single of them depends on every z here, right? Huh? And you could say that every z that every y that you consider is the corresponding row multiplied with this z, right? So for every single of them, so for every yk and zn, you have this partial derivative, right? So what you can say r is a function of all of these yks, right? And I am going to look into every single partial derivative with respect to yk. And when I calculated that partial derivative with respect to yk, I go ahead and see what is the derivative of that yk with respect to zn. So this is the vectorized form of the chain rule. So if you do that, then this guy is going to be the same thing. Dr hat with respect to or the partial derivative of r hat with respect to yk is what we have in our gradient. So we basically have it here. We don't need to calculate it. But what about the derivative of yk with respect to zn? What is it? Look at it here in this expression. It's going to be akn, exactly. Because that is it's a linear function. And only when I calculate only derivative with respect to zn, anything else is going to disappear, right? So this is going to be akn, right? And then you can write it down in this form. Everybody's clear what I've done? Yeah? So now I have the partial derivative of my loss with respect to one particular input at z, given in terms of my available gradient, partial derivative with respect to yk, times entries of that matrix. And we can simply do it much easier, because if you look at this expression, this is basically, again, an inner product. So I am inner producting this A, which is a vector when I change k, with that gradient. So you can simply write it down in form of this inner product. And if you just start stacking them next to each other, so for z1 it's going to be the first vector, for zn it's going to be the last vector, and you multiply them with the gradient, you can do the same thing as we did in the previous slides, a couple of slides ago, and then you can say that this is this matrix multiplied with that gradient, right? And now, anyone knows what is that matrix? That is A transpose. Great. I'm happy that you could follow. I couldn't follow myself. So okay, that's great. Thanks for answer. So that is basically the A transpose. So this is the transpose version of A, right? And you don't need to do this in order to get that this is A transpose. Why? Because you really need to only check the dimension. Yeah? So what is the dimension? Let me get back here. What is the dimension of this guy here? So I told you that y is k-dimensional. What is the dimension of the gradient of r hat with respect to y? k, because it has k different variables, right? What is the dimension of derivative of r hat with respect to z? And z is n-dimensional. N. So you need a transform which makes k-dimensional vector to n-dimensional vector. A is k times n, so you transpose it, it's going to be n times k, and then you're going to have this one, right? So you don't need to memorize anything. You always can see it by checking the dimension. So moral of the story, if you have z pass through one matrix A, you get y, and from y you get to r hat. As long as you know this gradient with respect to y, you can simply multiply it with the transpose of the matrix, and then you're going to get back to the gradient with respect to z, right? Clear? Yeah.
So if we were to relate this back to the I guess the A transpose here would just be the X transpose. It would be equal to X transpose if we want to find
Yes, yes. We're going to say, yeah, we're going to open up the neural network, and you're going to see it exactly. This is the purpose of doing those individual operations, right? Okay. So would it be fine if I take a few extra minutes to finish the last operation, and then I'm going to leave you for good? Yeah? Thanks. So let's just go for the last operation. The last operation is that I have a matrix A, and then I multiply it with X, and I get Y, right? So it's pretty much like the previous one. The only difference is that now my variable, instead of being a vector, is a matrix, right? You get the difference? So I have y, and if I have y, I can look at a as the variable, and then I multiply a with one vector x. So a is k times n, x is n-dimensional. When I multiply them, I'm going to get k-dimensional vector y, right? And then from that y, I am going to get my r hat. And then you might ask this question, what do you now mean by the gradient of r hat with respect to A, which is a matrix? You don't need to complicate things. I mean, it's a matrix. Just calculate the derivative, partial derivative of r hat with respect to every single entry inside this matrix. So you can basically think of it like this, right? So A going to have k and different parameters or entries, and you need to calculate the partial derivative of your r hat with respect to every single entry of this matrix. And of course, if you want to apply gradient descent on this optimization where you are just optimizing over A, you basically need to calculate your gradient with respect to A, and then you start from AT, then you just subtract it from this gradient, and then you're going to get your next matrix, and then you keep on updating that one. So everything is like before, just instead of one-dimensional array, I'm writing it down in two-dimensional array. Clear? And now, if you write down y, one particular output of y, in terms of x and entries of A, you're going to write it down like this. So this is basically the expression that I told you here. So this is the same product. The only difference is that now I am just looking at A, and I'm going to calculate the partial derivative with respect to the entries of A. Okay? Now, if you go ahead and do those calculations, so I have put this here for you. So you're going to start calculating the partial derivative with respect to one particular entry inside your matrix, and you're going to say that that entry is going to show up. It could potentially show up in every single y, so you are going to expand it in this vectorized form of the chain rule. But when you expand it, you're going to see that this yk, its partial derivative with respect to A of index j and n, is going to only show up when k is exactly j. So you're going to have this expression. Okay? If you are interested, just check it again at home. But what you can see here is that after doing this calculation, you're going to end up with such an expression. Okay? So your gradient with respect to the first entry of A, I mean like the first row, first column entry, is going to be your first entry in the gradient times first entry in your vector x. The second one